So today's lecture was supposed to be about the processes of research and types of samples and types of variables.
Sorry, crashed.
That's all right. So the process of research is that first we have some data from previous studies, so our previous experience, that kind of leads to what kind of hypothesis we want to develop. And then we test those hypotheses, and then these serve as a basis for future research, to either improve it or to change it. Can you go for one more? So we test hypotheses about the population that we want to examine, and then we propose what kind of experiment is going to explore that hypothesis, and we take a sample of the population. And then the analysis, we do examine them, and again, those results then feed back into future hypotheses, and also tell us whether we can actually infer some characteristics about the initial population. So statistics doesn't only play a role in the statistical test and in the examining the results, but also in the study design. So how we're going to propose experiment and what kind of experiment we're going to do in order to get the proper results that we can infer the characteristics about the population. Next one, please. So the population is the universe of items, is pretty much everything that we want to know, and because we cannot examine the population, we cannot examine everyone, we have to take a sample from that population, and that sample needs to be actually representative of the population. For example, if we want to study all the university students in Australia, we cannot take a sample of just medical students. We have to take different types of students. So the statistical inference is inferring characteristics or trends or relationships about the population based on a statistical analysis of a sample. That's why it's also important, first, that we pick the proper sample, and secondly, that when we do examine a sample, that we also take some baseline characteristics of that sample, so that when we do the analysis, we can actually compare it to the population that we want to examine. So to be sure that we can infer those characteristics that we examine, that they can be applicable to the whole population. So usually in the research, we develop two hypotheses. One is null hypothesis, which says that there is no real difference between our groups. And then the alternative hypothesis is that there is a difference. Usually we don't specify whether the difference is greater or smaller, and that's called a two-tailed hypothesis test. Another example is one-tailed hypothesis test, which says that our alternative hypothesis says that the difference is, for example, greater than 0. But in that case, the null hypothesis is that the difference is either smaller than or equal to 0. So single-tailed hypothesis tests are very rarely used in medicine, and if you do use them, you do need to have kind of a good reason why do you use them. Then, so when we develop a hypothesis, then we test it. And tests of statistical significance give us at the end a p-value, which tells us what is the likelihood of getting the data we got if the null hypothesis is true. So for example, if we get a p-value of 0.05, means that there is a 5% probability that our data, that we would get the data we got if the null hypothesis is true. So for example, if we would make multiple experiments with different samples from the same population, in 5% cases or less, we would get the data as extreme as we got if the null hypothesis is true. So then, according to alpha level, we then either reject or fail to reject the null hypothesis. In the recent years, there has been a lot of...
So by fail to reject, you mean accept, do you?
We mean accept alternative hypotheses. But because we are looking always from the perspective of null hypothesis, we can either accept the null hypothesis, reject the null hypothesis,
Or look for an alternative.
yeah. So yeah, the p-value is usually set as a threshold of 0.05, although it is not to be used in isolation. So when you do your research, it's very important what effect size you get and what confidence intervals you get, because p-value of 0.049 is almost the same as 0.051, and one means yes and one means no. So, and also if your sample size is large enough, you can detect a very small differences. And those differences may be statistically significant. However, they may mean nothing for a patient or for a clinician because they are such a small differences. So not only statistical significance, but also clinical significance is important. Then if you go on, we have two types of errors. One is type 1 error and the other one is type 2. So type 1 error is also called alpha error, and it's actually a false positive. So we're saying that there is a difference, while in reality there is not a difference. And that also corresponds to an alpha significance level that we set. So if you have a larger alpha, we'll have more type 1 error rate. The second error is type 2, which is also called beta error and it is a false negative error, which means that we say that there is no difference, while in reality there is a difference. And this corresponds to the power of our test. So if our test has a small power, it's lacking power, which means that we're going to have a higher type 2 error, and it means that we may not detect the difference even though there is a difference. And if you go on, so if we get an alpha level of below 0.05, we don't need to worry about the type 2 error, because then it means we are on the top row, so our data supports alternative hypothesis, so either it is true or it's a type 1 error. Then types of samples. There are different types of samples, and the samples depend on what kind of, the statistical test we use is dependent on what kind of samples we have. So we can either have one sample, so we just collect one sample and then compare the mean of that sample to a reference value that is either well known or been published before. Then we can have two or multiple independent samples, which means that there is no relationship between them, or it can be repeated samples. So independent samples mean, for example, a group of women and a group of men. While repeated or paired samples can be that it's a group of wives and husbands, so the wife and husband are related. They share the same beliefs, they live in the same environment. Or more commonly is we examine one patient before and after treatment. And as I said, the sample size depends on the type of sample we have. So for the independent samples, we usually require a larger sample size than if we have a paired sample. The samples can also be either balanced or unbalanced. Balanced means that each subgroup has the same number of people in there, while unbalanced means that some subgroups are larger than others. And types of variables, similarly as samples, also variables are dependent on what kind of statistical test we use. So statistical test is dependent on what kind of variable we have. So we can do certain tests with categorical variables, or certain with continuous. And there are three large groups of variables. So one is continuous, then is ordinal, and then categorical. So continuous carries the most data, and also there's the greatest variety of different tests that can be used with continuous variables. So continuous is always numerical, can be either positive or negative, and usually it's a decimal or a fraction of a number. And how many decimals we have, it doesn't depend on the type of variable, but it usually is dependent on the instrument that we measure with. For examples for that are age, weight, blood pressure, temperature. Then another numerical variable is discrete variable, which is again number. It can be positive or negative.
Just wait for Chandra to come back.
Oh, okay. I'm just looking out.
Yeah.
Yeah.
Perhaps you can give her another call.
Oh, yeah, maybe.
She might be out by now. Is Kumar with her or is she by herself?
Kuma's
Yeah.
I know Kuma's not around, so I'm assuming actually that he's with her.
Oh, she's not picking up. Yeah, they're
And then
together.
he's-
Yeah.
He's gone for a week,
Still asleep probably.
Is this a holiday or is this a conference?
It,
Mix. For Kuma, it's a conference. For Vij, it's a holiday.
but it was
Yeah.
conference a few days
Yeah,
ago.
yeah.
How's the writing up going, Lena?
Yeah, I'm drafting my conclusion chapter.
Oh,
So I've done all the result chapters actually, but Peter and Karen have yet to review all of them. So I've just got back Peter's final comments on the first result chapters. So I've got 3, one of which is published, which should be easy for them to have a look at. And the other 2. So experimental work, as far as I'm concerned, is over. But when they look at the results, and that was the majority of my time as well. I think I spent about 12 months looking at that. So it's all been a bit rough, but never mind. We'll see.
Good luck.
Thanks.
Yeah. No worries.
So yeah, discrete variables are numerical, can be positive or negative, but they have to be whole numbers. For example, that's number of children or number of admissions to hospital. And then ordinal variables are categorical variables, but there is relationship between the categories. For example, is a Likert scale. So how do you feel today? Very bad is worse than bad, is worse than good, is worse than very good. But we don't really know whether the difference between very bad and bad is the same as the difference between very good and good. That's why it cannot be numerical variables, but still is an order among them. For example, that stage of cancer or pain level or satisfaction level. Then another one is the categorical variables. So that's again different categories, but there is no relationship between them. So for example, color of the eyes. So it's blue, brown. We can't say brown is better than blue or twice as good as blue, or blood type. Another subgroup of the categorical variable is a binary or dichotomous variable, which is either yes or no. So it has only 2 categories. It can be yes or no, or it can be dead and alive, or female and male. And those are usually coded 0 and 1. And maybe a suggestion for research if you do in the future, if you have a categorical variable, always store it as categorical variable. Don't put it in the ordinal, because that you can always go from continuous into ordinal, but you cannot go from the ordinal into continuous. For example, if you collect body mass index, and if you actually want to analyze it as an ordinal, so whether, obese people have higher blood pressure than normal weight people, you can always, it's better that you store it as BMI, because you can always group it then in obese and non-obese. Well, if you collect this as obese and non-obese, you cannot go back and
That's
say
right,
which
I get what you
BMI
mean.
they have. And that is all. Do you have any questions?
So, coming back to, maybe there would be another session on how you calculate power. So how do you know how big a sample size you want?
Yes, I think there is another lecture about sample size. That's actually quite a complicated issue. But sample size depends on significance level, so on alpha level that you want to set. It depends on beta level, so it depends on power. And it also depends on what kind of difference you want to detect. So larger difference you want to detect, a smaller sample size you need. So smaller difference, it means that it's much less difference between the 2 groups, so you need a larger sample size to order to detect that small difference.
But aren't you predicting the size of the difference?
Yes.
So, you predict that it's going to be a small difference.
Yes.
or you predict it's going to be a large difference. So based on that prediction, you then determine what your predicted sample size will be.
Yes, in order to detect, because if your sample size is too small, then you get into the beta error. So even though there is a difference, you cannot detect it because you don't have enough power.
So is there sort of, I mean, it seems to me, I don't do research, but it seems to me that this is a bit sort of, you know, what's the science around predicting the sample size? I mean, you know, you know, if you just think it's going to be a small difference, or if you just think it's going to be a large difference, what sort of, you know, science can you have around actually making that prediction, you know, pretty valid?
That's previous research and previous publishment. So you can
Right,
see what
okay.
is their effect size, because to determine the sample size, you need the actual numbers, and you need also
Yeah.
the standard deviation around that mean value. That's why it's based on the
So like a
previous
pilot study
research.
that they may have done, and then from the pilot study you looked
Yeah,
at.
okay. So do you ever get into a situation where, you know, your prediction is wrong and you have to readjust your sample size? And is that sort of, you know, I suppose, standard practice, accepted practice in research, or do you have to actually start out with a fairly accurate prediction of what your sample size needs to be?
Usually you do need to start, but a lot of time researchers come to us and they have no idea what kind of size they
Yeah,
want to
yeah.
detect. So then comes back, go through the literature and just
Right.
find some idea. And then at the end, you may detect it, you may not detect it, because you don't even know whether your sample is actually similar enough to the sample that those other researchers did. Because if
So if you're therefore wanting to validate someone else's research, and I mean this occurs from time to time, doesn't it? Someone finds a big, I don't know, discovery or something, and you know it needs to be validated by other groups. So do you sort of basically then look at that study and mirror their parameters?
yes,
Yeah. So
Yes.
you do exactly the same sort of study to try and validate or negate
yes.
their conclusions
Yes.
or their research.
This is if you want to completely reproduce it. Otherwise, you can just see whether their findings are applicable to your study and to your population. And then you just try to mirror it as much as you can, but you cannot mirror everything.
And I guess you take into consideration their deficiencies, and then you try and repair their deficiencies too. So that's another nice way of validating. You sort of say, well, they didn't do X, Y, and Z,
Yes.
but we think it's more superior if we do X, Y, and Z.
Yeah.
And then you sort of do it. But one of the thoughts about, you know, when we think the differences are going to be small, so we have this large sample, the classic one is the randomized control trials. Like they sometimes halt the control trial midway when the results are so outstandingly different.
Or
Whether
like
it's
if
a
there's-
positive
if there's
difference or it's a massive adverse effect.
mortality.
Yeah. So we've had a few in the kidney world where they had to sort of stop it because of increased adverse effects. But
So,
then
but you have to really establish the milestones up front as to which you're actually going to look at the data and do some
Interim analysis.
interim analysis in order
Yeah.
for you to get to that point of
Yeah.
yes, continue, no, don't continue,
Yeah, that's
or
right.
you know, it's a bit like the you know, the renal denervation.
yeah.
You know, you know, the recent evidence suggests that it's actually
No
not
difference.
that helpful in, it's not harmful, but it's not helpful in managing uncontrolled hypertension. Although the people who are protagonists of it will tell you that they are concerned about the sub-analysis, and that, you know, when they did that and drew that conclusion, they were actually, there are a couple of variables that probably skewed the conclusion. But you could also argue, well, if you take those variables, account of those variables, you skew the conclusion back to the way you might think that it is helpful. So if you take out, you know, certain ethnic races, and if you take out operators that, you know, only do it for a year or 3 a year, and if you don't use a particular catheter which does, you know, 4 burn points, let's say, you know, there's no difference. But if you take out all those things and use the right catheter, there is a difference.
That's why usually in clinical trials they are very strict and you have to specify everything up front. And when you calculate the sample size, you calculate for one analysis only and all the others are subgroup. So
Yeah, that's right, sub-analysis.
yeah. And on sub-analysis, it's very hard that you stop the trial, even though
Yeah.
if you get the
It's
significant
usually the
result.
primary outcome that you pre-specify. That's the key.
Yeah.
Yeah.
Yeah, it's sad that the device, that trial didn't, the renal
Did not
denervation
really
one.
Yeah, that's right.
But
The other one's the renal artery stenosis one with the and stenting renal artery stenosis. That's also
that's also no different.
that's also no difference, isn't it?
Medical
Yeah.
therapy.
I remember it was one of those hot topics when we was
Yeah.
sitting for my exams and yeah. The problem with subgroup analysis is that it can show one of now I get my name wrong. A false beta error. I remember there was one study that we talked about in statistics where they used the use of aspirin in primary prevention in patients who've got some vascular risk factors but haven't had AMR, and then they did subgroup analysis, and just to show that how bad subgroup analysis is, they did subgroup analysis in terms of zodiac signs like Libra, and then they say that so if you're Libra, then it benefits more than the others. And the point of that was to show that this study was not powered for subgroup analysis.
Yeah.
And so then looking at various factors for whom the aspirin would benefit from that particular study was useless.
This was actually alpha error.
This was alpha error.
Yeah.
Yeah.
So if you repeat this, because when you do multiple statistical tests, like
Yeah.
in that subgroup analysis that they stratified into 12 different zodiac
Yeah.
signs, then you have to adjust your alpha level. Otherwise,
Yeah.
you will detect the difference even though there is none difference just by chance. Because if your alpha level is 0.05, it means that in 20% of your sample, you will detect the difference even if there is none.
So instead of saying it's the alpha level that's different, wouldn't you just do like a multivariate analysis to sort of remove? Yeah, but you're
Yes.
right that 0.05 should actually be 0.25 or 0.025.
Yes,
Yeah,
then there are
you can
different
do one,
adjustments.
yeah.
One of them is Monferroni,
Yeah.
that's the one that is most conservative and that decreases the alpha level the most. Otherwise, there are others that are a bit less conservative.
So I just lost you then. Can you explain that? I didn't-
So basically, but maybe Sarah should explain.
Yeah, if you do 20 different analyses,
Yeah.
then your
Yeah.
alpha level have to be for 20 times less than what is original. So if your original is 0.05, you have to
Yeah.
divide that by 20.
Okay.
And then you say that there is statistical significance only if the p-value you get is lower than the new calculated alpha level. That's called Monferroni
Because the
adjustment.
thought behind that is
Yeah.
the more groups you analyze, you're bound to get a difference just
One
by
in 20,
chance.
yeah.
You know, if you throw in 20 different,
Yeah.
you're bound to get one of them different, but it's just by
Yeah.
chance. So you take your p-value and you divide it by that 20.
20.
But that's a very strict, so that's
Yes.
Monferroni. Because
Yes.
then your p only becomes significant if you detect a p less than 0.001.
Yeah, that's right.
But that's how you should. So papers with multiple subgroup analysis,
Yeah.
then the more subgroups you do, you're just bound to find one
Yeah.
by chance anyway.
Yeah.
So whether it's really real or not.
That's why usually subgroup analysis are more for future research, just to kind of
Yeah.
Springboard to-
indicate the trends that may
Where it's going in the future and what
Yeah.
needs
Yeah.
to be done. Yeah.
Yes.
So, Shannon, can I just ask, where are you up to with your project?
Yeah.
Sort of where
So-
where we're headed?
Yeah. So in the last couple of weeks, we were just trying to look at how we can include the data, and then we decided that we're not going to. So I'm in the process of writing it up now.
Okay.
Yeah.
And did you present it at IMSAMS in any way? Did you have a
No,
poster?
because we didn't have enough
Right.
of that data. No. But next year, my plan is to present.
And what about Wendy? Where's she up to?
So Wendy's one, she presented her poster at the research here, and she presented, and she put a poster at the IMSAMS as well.
So she completed her project.
I'm not sure if she's completed. Yeah, not sure.
So when do you think you'll have the writing up done?
I'm hoping to do it before I leave here, so hopefully in the next couple of months. Yeah.
And your primary supervisor is
Hilton. Yeah.
Okay. And so what's the data telling you?
So it's so because I'm not going to change and much more.
Yeah.
So it'll be exactly what I
You
presented. So
presented
in,
before.
yeah. So it'll be the fact that additional units have improved mortality length of stay is difficult to say because it has gone up and down. That was quite difficult to draw a line through. And what was the other one? Cost benefit. I'm not doing it as part of this.
So how many years of data have you got?
1996 to 2000.
So when you're doing length of stay, are you doing that annualised?
It is day. No, it is
No.
for. So
You're doing the annual mean length of stay?
It's median length of stay, annual median length of stay. Sorry, I need to look at this again. Sorry, because I looked at.
Because
I looked
actually,
at
if you're doing length of stay, it
Yeah.
should, it should be going down. Because
So
before we introduced GMD, the length of stay was 9 days,
Yeah.
and so progressively it's come down. So,
So
I
if
don't
you
see
look-
why it would go up and
Correct.
down.
So if you look at
Unless you're looking at
between,
monthly variation.
so if you look from 2011
Yeah,
to 2014, it's coming down.
yeah.
If you look from 1996 to 2011, that's the bit that's going up and down. But since 2011 to 2014,
Well,
it's
so
become-
2011 was when GMD was
Correct.
introduced.
I can potentially present that, but then there was,
Wouldn't you put that in as an argument that, since 2011, when the other unit,
Yeah.
it's been a more consistent
Yeah.
length of stay, and it has, fallen consistently over that time.
Yeah.
Whereas before, because of the fluctuating workload
Yeah.
and the fact that, registrars, for example, had a large number of patients, and they often didn't sort of discharge them, expeditiously.
Mhm.
Some did, some didn't, and it was sort of fluctuating.
And I also broke up GM A and B, and then GM ABC, and then GM ABCD. And when GM ABC, so when there were 4 units, also the variation was a lot smaller, whereas the variation between A and B and C was quite big in the middle section. I was thinking of doing that, but then with the addition of GenMed C earlier on, there wasn't a huge change in median length of stay, and I was thinking, would I be criticized for cherry picking when GenMed D was added in rather than when GenMed C was added in?
Well, see, I can't ever remember a time when we didn't have
Genetic.
3 units.
Should I have it here?
I know, but I think there were sub-units within that.
Was there? But what would they be coded as?
I think there was, A1, A2. I can't remember, but I can remember the time where there were 5.
Oh yeah.
Is that okay?
I can remember the time where there were 5 units, and then there were 4 because the car. Which unit?
What year was this?
Oh, this is ages ago. And then there was.
5 units, really?
Yeah,
There were 5 units. There was one for each day of the week. There was the
car.
Carl unit on Monday, the Murphy unit, the Nile unit.
I don't know
And
how
I
they
can't
would be
remember
coded
the
as.
other 2. The Department of Medicine unit did Wednesday always. There were 5 units, and then it was redesigned. Jim Best redesigned. Then I think it went to 4 with a floating day. I don't believe there was, and then Jim Best redesigned it to 3. But, it went from 5 to 4 to 3 because it was A, B and C at that point. I don't ever think there was just an A and a B unit. I think there was always a sub-unit within it, yeah.
But were those subunits kind of grouped together so that they were known as either A and B, or?
Yeah.
I can't remember, but I really can't remember. I don't know whether it was sort of like, A1, A2, B1, B2 sort of thing.
Because in the coding, it's all A or B or
Yeah,
C.
well, they wouldn't have differentiated.
No.
But can you get the doctor? Who was the doctor? Were there different names for the doctors?
Yeah, we have the doctors.
Okay, give me the names of the doctors and I'll sort of try and tell you.
Yeah, we can do that next time we do have a data.
Yeah.
If you tell me the names of the doctors, I'll tell you what unit they belong to.
So this is the number of separations which was except in that dip there between
So where did
2002.
GMC come? When did Jim Best do the redesign? He did the redesign to 3 units. He went from 4 to 3. When was that?
2002.
2002.
Okay, 2002. We went from 4 sub-units to 3 units.
Yeah. And the numbers do sort of
Because
match.
Monday and Friday had to swing.
Yeah.
And I remember, out of your 3 weeks,
Yeah.
you had 2 weeks where you had 2 receiving days, and then you had 1 week to recover.
Yeah.
And that week you did the weekend, so it was pretty horrendous.
Yeah.
And so then in 2011 we got the 4th unit.
Correct.
Yeah.
Yeah.
But I think back in 1996, 97, 98, those, I'm sure we had 4 units. Because we didn't do receiving every second day. We didn't.
Yeah.
I remember that.
So unless because we filtered for Gen Med A and B. We filtered for general medicine.
Yes.
Yes, we filtered for general medicine, and under that it came out as Gen Med A and Gen Med B.
But if you can tell me the names of the doctors that seemed to be coded to A and some names of the doctors that were B,
Yeah.
I might be able to tell you how the units split off.
And this is the number of separations, and so if you look, so it's actually quite evenly split between. So if there were sub units within that, it was
Yeah.
quite evenly
Yeah,
split.
it's about a 50-50. So
Yeah.
that's right. Yeah, it's pretty even.
And it's about
50-50.
33%, and it's about 25% there.
Yeah.
And this is the median length of stay. So if you look from 2012 onwards, that's a drop there. So if you just draw a slope there, then yes, it goes down for all 4 units. But between that, it's up and down for all 4 units. So I was thinking of doing that, but then I'll maybe accused of cherry picking because C was started there. And if you do it for all, this is for the whole year. This is the median. For the
Yeah.
whole, yeah.
For the whole period that
For-
you tested. But that's a nice.
So if you look at from 2012 onwards, from 2011 to 2012, we went up a little bit, and then but from 12 onwards, it's a
Yeah,
huge
but I
drop
can see
there.
how you won't get any difference because you got low peaks at 2006.
Yeah. And 2002 was when GenMed C was
It's interesting how you got some years where it's that low, like 2006, like really? Did you really?
That
Well,
was
2002 to 5, it's probably higher also because of the EMU.
the EMU, and because the short stay.
If they
and-
were mainly patients who were a day or day and a half in there, they would bring the median value lower.
Mm. So was it EMU in 2006? Yeah.
There was, but it's the coding is all like emergency consultants, and there were about 1,000 patients in EMU. So if you add 1,000 to 2002 and 2003, you will see how they will go to 3,000, more than 3,000. There'll be a huge peak there, but that's because like short stay patients
Would be there.
would be in there.
But in
So there
your
were-
other graph with the length of stay, in that 2006 when
Oh,
it
pretty
really
hot. Can you
dipped
turn
down,
it down
do you know
again?
if you had
It's getting hot.
Oh, it's getting hot.
do you know if you had
Sorry,
those EMU patients added in there or those
No,
are
no,
without
this
that
is-
1,000?
this is
So
without.
that
Without.
1,000,
So this is
right?
all without, because we decided I didn't modify anything because it was if I added the numbers,
Yeah.
then it'll be like 1,000. Like it's like 900 something.
Yeah.
Mm. And if I took the EMU patients, so EMU patients who had the general medical physician coded, you only get like 30 or 40 out of that 1,000.
2006 was actually my year of HMO3s.
Oh,
My-
HMO3.
My fellow registrars, maybe they discharged everyone and he's gone.
Yeah.
Out! I don't know why.
It's because, and then emergency, the coding had changed so much. There's EMG, there's ECC, there's EMU. There's quite a few different emergency codings, and ESS now. So now there's two major coding, EMG and ESS, and yeah, and they all stay in emergency. The moment they come up, they're under unit. And then this is my seasonal variation, which shows in winter it peaks, and there's a chance of comorbidity, which means we are getting more comorbid, bigger proportion of more comorbid. Yeah. So the only problem is that middle bit, and this mortality bit is quite good. That does, yeah.
Yeah, but the mortality data is nice.
So this is quite good as well to show that in the last few years we're getting more and more complex patients. Yeah. So this is
Alright,
the,
okay,
the main problem is this one.
Yeah. Right, well, if you can give me some names, maybe I'll be able,
Yeah.
be able to recall it.
Which B1, B2, B.
Yeah, if you have a look at Evo's book, does that tell you anything about that?
Which one?
Evo Vala's book on the history of medicine at the hospital.
Is there
one?
Yeah, he wrote a book.
I have not. Where's the book? In the
It'll
library.
be in the library.
Evo Vela. Yeah.
Thank you.
Okay,
Thank
thank
you.
you.
Yeah, thanks, Sarah.
Thank you.
Thank you. Sorry?
How's there a spike there?
The other thing is, I think GenMed A.
GenMed D has a spike just last year. What was that?
GenMed. Which
In
one?
this one?
Yeah, the yellow one.
I don't know.
There's a
GenMed
spike
D.
right up.
Went up a little bit, yeah.
The other thing is, in 2006, I think Wilma might have been head of GenMed A.
Could have been. Could have been.
Because she was always the.
Yeah.
Yeah, because mortality is so low, it means that all the sick ones were just out.
Alright, see you now.
Okay,
Yeah.
thank you. Am I done? And then, thank you, Billy.
No worries.
How do I exit this? Thank you, Sarah.
Please just text it.
Oh, good. I was wondering whether she's okay because she hasn't
Yeah.
responded
She just
to any of
texted.
the
Yeah,
emails
the,
either.
the internet at the hotel, she said, wasn't working great. So there's some trouble connecting to Skype.
Thank you, Billy. Do you want
No
me
worries.
to help you with anything?
No, I'm okay.
You
Thanks.
sure?
Yep. Thank you.
I'll wait for you and I'll open you the doors.
No, it's okay. I'll borrow Trish's